Hello everyone, my name is Mark. Welcome to my Calc 3 videos. And today we're going to be talking about maximum and minimum problems, and particularly local extrema. So let's talk about critical points. I'm sure you've heard of it. So the criteria for critical points for one variable function is the first derivative equals to 0, or the first derivative does not exist or undefined. So what are the conditions for the critical points for two variable functions then, right? So the difference is you not only have to have fx equals 0, you also need to have fy equals 0, or alternatively, you can have fx or fy dne. Only one of them needs to be dne. So where should you apply for the second derivative test of a function regardless of a single or multivariable, right? I hope you remember when you apply a second derivative test, you always apply them at your critical points, right? So you always apply them at critical points. So that is the the refresher on the critical points concepts. So here you have the second derivative test for two variables, right? I want you to recall the equations for second derivative test for two variable functions, as well as all of the possible conditions and outcome of this test. Okay? So let's go ahead and pull up my handy dandy notes. There it is. So we just talked about the conditions for critical points. And then this is yours, and then this whole jumbo of thingy is your second derivative test for two variables. I'm sure you've learned about it. I'm just gonna go through this really quickly. Right, so you need to calculate the discriminant, which you have the equation that right here. If your discriminant is greater than 0, good news, extrema exists. If your fxx is greater than 0, local minima, fxs is smaller than 0, local maxima. If it's smaller than 0, then it's a saddle point, right? It's neither maximum or minimum, and if it's 0, it's inconclusive. So the one thing that helps me memorize this second derivative test is using the idea of curvature. How am I gonna do that? So right, so in your curvature, when we're learning about curvature, right, so this is a local minima, right? It's a concave up, right? So concave up, that means the second derivative is greater than 0. So it's the same idea right here, right? So if fxs is, think of it as the quote unquote the curvature, even though it's not really the curvature. But we are kind of like, we're using that similar idea, right? So if this is curvature, if it's greater than 0, it's concave up, then it's local minima. And if it's concave down, you have a negative curvature, right? So you have the second derivative is smaller than 0, so it's going to be a local maximum. So that's how I can use the idea of curvature to help with me the memorization. Okay, and then one more thing about second derivative test is a true or false question. So true or false, this test is also valid if fxs is replaced by fyy. That is true, okay? I don't know why, but that is how that is a viable option. So if you want to try fyy instead of fx, go for it. Okay, so let's go ahead and take a look at an example. Open my one pager, open my solution sheet for you. The function, right, attains its local minimum at, right? So reading the equation problem, we can see that it's a local minimum problem. Easy enough, right? So it's a maximum min problem, particularly it's a local extrema problem, right? So another way we can tell, right, we'll talk about this in more detail in the next video, is how to differentiate between local or aka relative extrema compared to absolute global extrema. Okay, people get confused a lot. So to identify if it's a local extrema problem, it's not only the words, but also they gave you no bounds, right? So this function exists on the real axis, on the real number, right? There is no any sort of constraint that's confining what the function should exist within. So with that said, let's go ahead and start solving the problem. So first thing is we're going to find fx and fy. So step 1, right? So we're going to have fxy equals to 6x squared plus 3y squared. Oh, never mind. Fxy, yep, that's correct. And then we're going to have minus 16, right? So fx equals to 12x, and then fy equals to 6y. So that's step 1. Step 2, we're going to find the product points where fx and fy equals to 0. So fx equals to 12x equals to 0. That means x equals to 0. Fy equals to 6y equals to 0. That means y equals to 0. Right? So therefore, our critical point is 0, 0. And then step 3, find. We're going to find fxs and fyy and fxs or fyx, right? In your maximum minimum cases, your maximum minimum problems, these two values will be the same. Chances are they will be the same. I don't think you will be wrong with going for each one of them, but just keep in mind they can be different. If like it's not a function that's not absolutely guarantee you these two will be the same, right? So but in maximum minimum problems, most of the time it is, and I don't think you need to test both of them. Okay, let's keep going. Fxx equals to 12, fyy equals to 6, right? And then fxy equals to 0. Boom, easy enough. And step 4, we're going to assemble the discriminant. Right, so the discriminant of x and y equals to f. So this equation, let's go ahead and highlight it in red. That's useful. So this will be 12 times 6 minus 0 squared equals to 72. 72. Okay, so step 5, we're going to test the discriminant at the critical points. So, and then I'm just going ahead and copy and pasted my second order notes for you. Right, so, and in this case, in our problem, the discriminant is greater than 0. That means extrema exists, right? So extrema exists. And then, if we pay attention to the fxx, it's 12, right? So that means fxx is greater than 0. It's a local minima, right? So there you go. There is your answer. It's a local minima at the 0, 0. Right? So there you have it. The answer choice is C. Well, actually, so I just showed you how to apply second derivative tests for any type of problems that's asking you local extrema problems. But for this particular problem, I want you to take a look at the equation. What is this? What is this? This is a paraboloid, right? This is particularly, this is a paraboloid centered around 0, 0. The surface is a parabola centered at 0, 0. what that means, right? Parabola, right? It's a parabola centered around 0, 0. Right? Local extrema automatically exists at 0, 0 on the horizontal coordinate, right? We don't know. I mean, heck, we can figure out the y coordinate if we want to. Technically, it's negative 16. But if you read the question careful enough, you would realize you don't even need to go through any of this. But I showed you anyway, just for the sake of showing you the process to apply for any type of problem. But there's clearly a shortcut to this problem to arrive at the correct answer, which is 0, 0. Okay. So that is how you can apply for second derivative test to find maximum minimum problems for local extrema problems. So it's again, it's kind of the same idea, right? It's kind of the same idea as you have learned in Calc 1. You're using second derivative test, right? Critical points, and then using the second derivative test to find the critical the values at the critical points. Just a bit fancier. So so that's what I have for you for this video. Thank you very much for watching. I hope you learned something. I hope you can master the process, not the numbers, and I will see you in the next video.